Sally the scientist is tracking turtles that are colonizing the many islands of the Florida Keys. These two islands, Fun Island and Great Island, Sally calls them F and G for short, have no turtles. One year, let's call it turtle year 0, 3 turtles managed to swim to each of the 2 islands. She returns in 1 year to see how the populations have grown. Wow, the turtles on F have increased to 5, and the turtles on G have increased to 6. A year later, and the turtles on F have increased to 7, while the turtles on G, wow, have increased to 12. She keeps checking year after year, and this is the data she collects. Can Sally find some patterns? Let's look at F. The turtles increase at a constant rate. Sometimes we call that a common difference. We started with 3 turtles and added 2 for however many years have passed. So if 10 years pass, we would have 2 turtles times 10 years plus the 3 turtles we started with. That's 23. If X years pass, then we have 2 times X turtles plus the 3 we started with, and wow, that's a linear function, y equals mx plus b. Sally is starting to understand what's happening. If we graph the function for turtles on island F, we get a straight line, of course. Remember, if the values are created by adding or subtracting a constant, this is a linear model. Cool, well what about the turtles on island G? Here the turtles appear to be doubling every year. So instead of adding a constant amount, we have an annual multiplier, times 2. So for example, to find the turtles for year 7, we multiply 3 turtles we started with times 2 7 times. We can use an exponent to write that. Wow, that sure looks like an exponential function. Y equals a times b to the x. Sally is on it. And here's the graph of the function. Sally's research shows us that every exponential growth function with a multiplier above 1 will eventually exceed a linear function. Eventually there will be more turtles on island G because exponential growth always beats linear growth. Remember, if the values are created by multiplying or dividing by a constant, it's an exponential model. Sam is Sally's colleague, and he's always studying islands in the Keys. He's studying Pretty Island and Quizzical Island. Here's his data for the turtles on island P and Q. What happens to the turtles on island P? The data doesn't look linear, we don't have a common difference. Maybe there's a multiplier at work, which would make this an exponential function. How could we find that? Let's divide each y value by the previous one. If that common ratio holds up, we've found a multiplier. Yup, there it is, 2.5. Here's the equation. And a bigger multiplier means there will eventually be more turtles on P than even G, the other exponential growth island. How about Quizzical Island? Sam missed his data collection on year 0, but on year 1 there were 10 turtles. On year 2 there were 40, and on year 3 there were 90. Those numbers are quite quizzical. There seems to be a relationship to the number of the year. Yes, the y values are just 10 times the square of the year. For 9 years, there would be 10 times 81, or 810 turtles. Quizzical. The function is y equals 10x squared. Do you recognize that as a quadratic function? Y equals ax squared plus bx plus c. B and c are 0, but it's still quadratic. Here's the classic shape of a quadratic, symmetrical. Which turtle population will eventually exceed all the others in the long run? You might think the quadratic, because it grows pretty fast, but nothing can compete with an exponential in the long run. A quadratic has an exponent locked at 2, while with an exponential function, the exponent is x, and x can be as big as we want. We have common difference to detect linear functions, and common ratios to detect exponentials, but what about quadratics? One trick is to use the difference of differences. Find the difference from one value to the next, and then find the difference between those differences. If the differences of the differences are constant, then we've got a quadratic. Sam confirmed it. Remember, if the differences of the differences are a constant, you've got a quadratic model. So linear functions have a common difference in consecutive y values. That's the slope. Exponential functions have a common ratio, the multiplier that makes exponentials grow faster than anything else. You can always detect quadratics by finding a constant difference of the differences. Eventually, exponential growth always exceeds quadratic growth, which exceeds linear growth. Thanks for your research, Sally and Sam. So, which island will have the most turtles in the future? The exponential growth function with a multiplier of 2.5 will make Pretty Island a great place for turtle fans to visit. But you really have to like turtles because they will be everywhere.